Swayam Prabha. Digital India. Educated India.
What's the first supercomputer developed in India? Huh? Okay. And developed by Sirat. So he's the right person to give this talk, right? So.
All right. So Preeti gave an apt introduction, and this is the agenda. Very simple: the past, present, and the future. Okay. So I will discuss what have been the efforts so far, what is going on, and what we can see in the future. So beginning with the past, it's not that before CDAC came into existence, no efforts were made, but TIFR, if I am not mistaken, Bombay, they tried to build a system for their own use, which can be called as not really a supercomputer, but a computing system which was dedicated for their use. But the real challenge came in when we wanted it for India wanted it for a bigger purpose, like predicting weather. And at that time, supercomputers were, even today, they are dual-use technology in the sense that one can even do nuclear simulations and things like that. So the US government at that time felt that we can be used for other purpose, so it was denied. And at the then Prime Minister Rajiv Gandhi, he said that why can't we make it ourselves, and thus that effort started with Dr. Vijay Bhatkar being given the a 3-year time with 30 crore as a budget, because that was the price of the supercomputer that we were going to buy at that time, and that's how it started. And I have once interviewed him, and he said that at that time none of the team members had ever seen a supercomputer, how it looked like, and they took up the challenge of building it from scratch. The hardware, the system software, the applications, everything was to be made in India through an indigenous efforts. And that's how 300 man-years were required to build the first Param supercomputer, that is Param 8000, and that was delivered. And over the years, like starting with 8000, then we had 9000, that was a slightly better version with a better CPU and more compute power. And we kept, some of them are not mentioned here, but for different versions using i960 and other processors were made. But at that time it was found that the hardware keeps changing very fast, and those days we were not in the best part of world where getting access to all those details and bringing newer hardware was a bit difficult. So starting with Param 10,000, which was a 100 GF machine, what we decided was, like the other day I told you, we will use a cluster of workstations. So CDAC concentrated on building the network, which I shall describe later. So was Param Padma, which was built on Power series Power 4 CPU. Then in between we made what is called as Garuda grid, which is not much in use now. The concept was that, like you have electrical power, you just tap in and you get the power. You don't know where it is actually generated. It could be any of the power generating stations. Similarly, can you have a grid of computers where you want a compute power, and through a software framework or access method, the required compute power is made available to you. So that was the concept of grid, which does not exist in much seriousness now, but there is a different way of doing that. I'll explain at the end when I describe the National Supercomputing Mission. So Param UR2 was, which is currently, the best computer that CDAC has, about half a petaflop system that is at Pune. And then in between we had something called as Param Shavak. I will describe that, which is not really it's not in the increasing, doesn't fit on that line, because it doesn't have power which can compete with the other supercomputers there, but it's a different concept that shall explain. So this is what CDAC has been doing, and the future is NSN, which I shall describe in the subsequent slides. So having seen the big picture, I'll just put you into what Param 8000 did. So it was, as I mentioned earlier, the goal was to have in 3 years time, in less than the price of buying a supercomputer, developing our own. So it had, at that time I mentioned that on day one also, that Param 8000 was just 1 gigaflops, that is 1 into 10 raised to 9 floating point operations in a second. And in fact, you can try this. There is this LinPack, which I mentioned the other day also, that is used to rate the top 500 supercomputer, and Android version of that is also available. So you can download it and run it, and you can see how much is the floating point power, HPL power, that your particular phone has. Most likely it may have 8 cores or some 4 cores or 8 cores of ARM. So people have written, basically that is a source code is available, and people have compiled it for Android, and it's available in open source. So that you will find that your phone has more power than 1 gigaflop supercomputer computing power that Param 8000 offered. So it had proportionate primary memory depending upon how many CPUs you use. Then IO bandwidth, which was used for connecting secondary storage, graphics was part of it, and high-speed network interface. So this was the hardware which was built using what was called as an InMOS make transputer. So that transputer's number was T800. Thus, the first supercomputer was called Param 8000. And incidentally, Param, that is an anagram of parallel machine. All right. So what I was trying to say was Param, the name comes from parallel machine, Param. And Param also means supreme in Sanskrit. So thus that name was born, and 8000 came in because it used a processor called T800. So not only the hardware was made, but parallel programming environment and the applications which could scale on that were demonstrated. So that's how that 300 man-year effort came in. So think its architecture, it used InMOS transputer. It was a distributed memory architecture. The good thing about this transputer was that it had links in it which could directly connect to other transputers. So 4 links were inside that. So no other processor, in my opinion, has that kind of architecture. It was actually meant. So, and that transputer word comes from, just like a transistor can be used for building a computer or an CPU, this transputer can be used for building a supercomputer. So it was meant to be used in a massively parallel processing kind of architecture, and it was really a good architecture. Another reason for choosing this InMOS transputer was that it was a British company which was making it, not a US company. So we already had a bad experience with the US government, so that was a strategic decision why this InMOS transputer was used. So amongst the node, you could transfer messages. So very similar to what you do today on a computer-to-computer communication, same thing was happening between CPU to CPU communication. And it was like a standalone system, and a personal computer could be connected to it, which was a host, and from there you could fire the job. And it could have PCAT, which was the architecture for desktop computing at that time, or Sun Workstation made by Sun Microsystems, which is now taken over by Oracle, and Microvax, which was a company called Digital, which was taken over by Compaq, which was then taken over by HP. So these were the computers that were available at that time. And it also supported multi-user facility like you do now. Multiple users are running their codes. Same thing was possible there. But the nodes could be fragmented and allotted to a particular user, and he could run his job there. And one partition assigned to one user that's dedicated to him. If that job gets finished, it comes back to the pool. And it could accommodate heterogeneous nodes, like there was a compute engine, disk node, graphics node, even vector nodes. Now you know what vector is. and DSP nodes. So it was quite a forward-looking architecture at that time, and it was made totally by Indian scientists who came together with a goal of delivering that computer in 3 years' time. I still remember, I mean, I was not there at that time with CDAC, but I still remember that time they used to have days to the mission, like today it's 100 days, 99 days, and they would time their deliverables in a very professional manner. So I will skip through rest of those. I straight away came to Paramyua, which was the, maybe I think it was made in 2008. So it was used on, it was like a cluster now, a pure cluster, based on CPUs, which was Xeon processor. Tigerton is the internal name of Intel, and it had Paramnet 2 as Paramnet 3, sorry, as the clock network. So clock network is something which gives dedicated bandwidth between any two nodes of that network. So in the morning we talked about star, and we also said that if the main node fails, then the entire network collapses. But the good thing about star network is every node is one hop away from the main networking fabric that you have. So to overcome that problem that it should not fail, you built resilience into that network such that the main switch does not fail. So we had all those features in it. I will describe a little bit of it later. And it had a communication processor. So the concept of communication processor is like you must have, you must be aware that there is something like a TCP/IP stack for networking. So this networking stack is nothing but a program which runs on the CPU itself. So you have when you have multi-core CPUs, one of the core is used for running this networking stack. But when you have a specialized network like this, the entire stack is run on the card. So CPU can only do the work related to running your code. So that is also called as, if you have heard, called as offload engine. So that the stack is entirely offloaded to the network card, wherein the MPI driver will say that in this memory location, this is the size of my message, and that entire message is fragmented and sent across with reliability to the other side. So that was the concept of communication processor, and it had a 48 port switch, and using that a system was built which was 54 teraflop compute power. So this is what I was referring to. So this is the networking card that you have, and there is an FPGA behind this fan, and the stack runs on it, and like this cable connects from this to the one of these ports. So there are 8 into 6 leaf cards, and thus you connect 48 ports to this. So then it has got its own processor, crossbar, packet forwarding engine, and it uses standard Ethernet cable, but the protocol stack is entirely designed by CDAC, which is lightweight and high bandwidth. And this picture shows that these are the racks in which in one rack there are 9 computers, and thus you can connect 48 such computers using this switch. Okay, so that was in Paramyua. So this is Paramyua 2. What we did in Paramyua 2 was that after 3 years time, I think after 4 years time, we just replaced all these nodes with a better nodes. So what happened was, same electrical power that it used to consume, in that we got 10x compute power. So this is something that on the first day also I mentioned that today the focus is towards, for a given watt of electrical energy spent, how much compute floating point operations can we do. So if you can do it more in a given watt, the trend is towards having more and more floating point operations to be done. So that is what Paramyua did. We had about 10x compute power, half a petaflop up from 54 teraflops by using the same, everything remained same, only by upgrading the compute hardware, compute nodes. Okay. So it, as I mentioned, it was upgraded from 54 to 524, and because we simply changed the nodes with a better version of CPU. So this will have more number of cores, so its compute power increases. Then other thing that now this is a defunct, but Intel had what is called as Knight's Landing. So it uses a architecture called many integrated core called as MIC. So this is very similar to GPU, but Intel, what the good thing about this is this KNL's instruction set is compatible with Xeon's instruction set. In case of CUDA, the instruction set of CUDA is different. So there can be a binary compatibility between the CPU and the accelerator. So that was a good thing, but somehow after a couple of versions, this architecture did not get through, because Intel, I think, is planning to have more number of cores in the Xeon itself. So it approaches like this, I think, had 54 cores in KNL, and the CPU would have something like 8 cores. So the total, there are about in 288 nodes, there are about 30,000 cores, and this Param UR2 is connected to NKN network. So currently it is being used by many researchers all over India who become technical affiliates of this Param UR2. It is housed at something called as National Supercomputing Facility. Okay, so any questions? Okay, so this is what, yeah. So it's National Knowledge Commission, National Knowledge Commission Network. That's how NKN stands for. It like every institute, government funded research and educational institute in the country is linked to it. So it becomes easy to access any computers which are, or any other, even emails, many things are possible over it. And currently I think it is in process of getting upgraded also, so more bandwidth will be available on this. So coming to the present. So here I have listed the top 10 supercomputing systems in India. So there is a website topsc. Earlier it was to be maintained by Professor Satish Vadiyar at ISC. So now he has handed over to my colleague at CDAC Bangalore. So as you know, the top 500 worldwide list is published twice. So similarly, whenever that list is released, 1 month after that, this list is released. So the current list is dated, I think, July 2019. So out of this, as Preeti had shown on day 1, these first 2 supercomputers are in the top 500. Rest of them were once upon a time, like Param UR2. When it was made in 2013, it occupied 69th rank. That 69th rank, next list became 169th, then it became 250. Then it became 365, and then it went out of the list. So like this will remain again for a few lists, and then they will also go out. So that is, as I mentioned on day 1, it's a moving target. So you can see here that now there are 2 numbers here. One is called as max, and another is called as a peak. So max is like how many cores you have, what frequency at every core runs, how many floating point operations can happen in 1 clock cycle. If you multiply all these 3 entities, you get one number. So this is a theoretical peak. That this IITM's Pratyush can do 4 peta floating point operations in a second. It is capable of doing that. But there are various reasons why a particular program cannot extract that, because some of the things were mentioned in the lecture by lecture on architecture, which said that there is instruction level parallelism, but it may not be always possible to run all the execution units at their full capacity. So how do you figure out what is the usable capacity? So for that, there is a program called HPL that I mentioned to you, which you can run on your Android phone. So using that HPL, high performance LIMPAC, it runs and it gives a number, and that number is this. That is 3.7. So the ranking is done based on the performance obtained. And we can say that this is the efficiency between the maximum possible and what is actually extractable. So this is extracted using HPL. If you run other benchmark, there are few other benchmarks, HPC, G, etc. They will give a different number. But some of them work on conjugate, does matrix multiplications and few more things. So source code for that HPL is available. You can go through it and you will know what all it does. So here we have listed these 10, there are about 35 that are mentioned in that list, out of which I have taken 10. So a quick look at what those systems are. Like it is this one, the one at IITM, it is used for, it's not a publicly available, it is used for ocean atmosphere climate research system research. So this is what is called as a coupled model, that they are working on a coupled model which links the land as well as the sea, and which is useful for knowing how the weather will be predicted. So it's based on Cray system, which has got about more than 3000 CPU nodes. Like I mentioned ParamNet, similarly Cray has their own interconnect called as Aries. So that connects, that is a system area network used in this, and it uses Lustre parallel file system, about 10 petabytes, and the tape capacity is 30 petabytes. Then this is National Center for Medium Range Weather Forecasting. It comes under IMD, or Ministry of Earth Sciences. So these two systems were installed together at the same time, but they are split. One is used for this solving this problem, whereas this one is used for monsoon mission. So India runs a program called as monsoon mission. As you know, Indian economy is very much dependent on agriculture, and agriculture can survive only if the rains are good. So there is a attempt to model the monsoon and predict. Every year you will find that IMD in the month of May, it tells you what is going to be how much percent is going to be the monsoon this year. Like last year, I think they had mentioned almost 98%, and it actually turned out to be 103 or 105%. So we have how does that percentage comes in? Over the past 100 years, data is maintained, so you know what is the average monsoon that India gets on various parts of the country, and how much of that is going to fall in a particular year. So this is monsoon mission. Climate change, of course you know all of this. They are trying to figure out based on greenhouse emission, etc., how the climate is going to change. So it is exactly replica of this, less number of CPUs, less number of sized storage, and you will find that they have maintained a ratio of 1:3 between the usable storage and the backup drive. Then this is at IISc. So this is again a Cray XC system. Everything is same, but it has got Xeon Phi nodes and GPU nodes also. So now you will notice here that this is completely a CPU class system, because the weather forecasting code has got good affinity towards CPU only system. Whereas if you notice here, this is a system that is used by students and researchers at IISc. So they is heterogeneous in nature. Some nodes have Xeon Phi, some nodes have NVIDIA's GPUs. So they will run a variety of workloads. So similarly, some of the systems in Param UR2 are also upgraded with GPU nodes, because depending upon what a user wants to use, that can be made available. So again, it has got 12 petabyte Lustre file system. This was the Aditya got upgraded to Pratyush. So it was another system with, they were doing the same work on it, which then they migrated to the new one. But this is used by Inquise and other weather forecasting teams currently. Yes? Pardon? All of them are cluster. All of them are clusters. Okay? With hybrid architecture, you can say. So hybrid architecture comes in like GPUs or Xeon Phi, because they give more compute power while consuming less electrical power. So they are more power efficient. Then this India Lattice Grid Transformation Initiative, they also have got a Cray system with less number of nodes. Param UR2 I described to you earlier. So it uses ParamNet and InfiniBand. Again, it has got it's a hybrid architecture. So that was a quick look at what these systems are used for and what are the number of nodes. All of them are clusters. Okay, now I would also, there was some query about this, so I wanted to address this bioinformatics users here. So CDAC has got a dedicated facility called BRAF, Bioinformatic Research and Applications Facility. So in this, there are three computers. One is called as Biogene, other is Biochrome, and I forgot the name of the third one. So now this is more like a dedicated facility for bioinformatics users. And in case you are interested, they have a conference called as Accelerating Biology every year. So this year it is in the month of February. So you can visit CDAC website, cdac.in, on the homepage itself. And for students, I think they charge 5,000 rupees. The early bird price is over. Otherwise, you could have registered. With 3,000 rupees itself. So they have got lot of. I am just noted here. You visit that website and you will know what are the tools available, like sequence analysis, starting with Smith-Waterman, and so many things are available. And they have what is called as problem solving environment, meaning you don't have to worry about writing codes. You can straight away choose the problem solving environment, choose some initial parameters and run your code. And one more thing I will explain later, Biogene uses what is called as a reconfigurable computing card. I will explain that later. So this speeds up the sequence search very, very fast. So these are some of the unique things. If in case you are interested, you can approach them and use them. And you can attend that conference. It is an international conference, and there you will get to interact with many of your colleagues who are working in the same field. So this is the URL. Anyway, these slides will be shared with you, so you can click on this and figure out what all they offer. Another thing which is unique, which I would like to tell you, there were requests for knowing this also, is Param Shavak. So why did we make Param Shavak? Is because it is a supercomputing in a box solution. So it looks like this. It's like a server class machine which you can keep it in your lab. It doesn't need any air conditioning, anything. Normal air conditioning would do, unlike the precision AC that other supercomputers need. So the reason why we made this was that it will have exactly the same environment that you would see. It would have the same environment that you would see on a bigger supercomputer, and I will show that in the next slide. But the compute power that you get is about 3 teraflops. It has got one server class motherboard with 2 sockets, each having 18 CPUs. You can also take HPC card called as GV100. If you put that, you get 7 teraflop because CPU plus GPU. Other option is, if you want like this deep learning model, then the base system is same, but you get in single precision, you get about 9 teraflop by using P5000 card for DL, that is from NVIDIA. So NVIDIA has 2 cards, one for HPC application, other for the applications related to AI and ML. So who would like to have this? One is, suppose you are a researcher who want a dedicated facility for yourself, which you don't want to share with others, and then you have a low budget and you don't want to waste time in queue for a bigger system, and this much capacity could be sufficient for you, then you can take it. Other important thing is it's useful for training, because you don't need lot of compute power. You just want to scale, you want to see whether your algorithm is correct, does it work. You can do that here, and the same code as it is, like you might have, I'm not sure whether you tried it or you can try, the code that runs on Param Shavak that you have access to, as it is, will run on Param Shrestha, which is a 100 teraflop facility. If it can run on 100 teraflop, it can run on 500, it can run on a petaflop system, because you have to just scale up, add more nodes, add more data. So there are three versions, out of which 2 are very popular. Third is virtual reality, which is a Windows based system, but these are the ones you may be interested in. So in case you are interested, you can contact me or Sandeep, not now, even later, or you put across your in charge of your department to us, and we will help them in taking this forward. So it has got everything here right from, this is very similar to the stack that I showed you day before yesterday. So it's a hardware, storage, operating system, device drivers, everything is there. And why it is useful for training is because it comes preloaded with all these softwares, open source software. And there is a how to use kind of, there are videos how to use it. So it's like a small system which gives you all the facilities that you would otherwise find on a high-end supercomputer, but with a less amount of compute power. That is what needs to be kept in mind. Okay, so I will then briefly tell about, because we are talking about what supercomputing activities happen in India, I will quickly run through the indigenous technologies that are used in Param. One is the ParamNet and other is the reconfigurable system, so I will explain this. So ParamNet, like from the first Param that we made, so till now we have been making various versions of that, and again I will not get into nitty-gritties, but one thing that I would like to point out is that this CCP2 coprocessor that we made was one of the first, if not the first ASIC, but one of the complex ASICs designed in India at that time. When it came in 1997, at that time Pentium was the contemporary processor and it had almost that many number of transistors. So it's a quite, so these coprocessors are the one on which the stack runs, so that the main CPU can need not spend time on running the stack. So in various versions of Param they were deployed. So what does it contain making a network? First you need a chip. So this is a ASIC, but now we are using FPGAs, because the reason for going for ASIC at that time was it was giving much better performance than FPGA, which was needed for building that network. But now FPGAs give you equally good performance, except that in low volumes FPGAs are cheaper, but if you want to make high volumes, then ASIC is the way to go. Then using this you build interface cards like this. These interface cards go into the nodes of the cluster, and you form a cluster by connecting these cards to a switch. So there are various versions of switch, and coupled to that you need a lightweight protocol stack. So in this there are, the stack is also mentioned, like VIPL was one of the industry standard, DAPL, socket direct programming, or TCP/IP. So these are some industry standard stacks, because of which then your MPI will run on top of this. So this developing the stack is also important because it closely works with the hardware. So what are we doing next? We are doing the next version of ParamNet, wherein we are, the topology, as I said in the earlier one was star. In this it is going to be a torus. So 3D torus. So this is how that complex card looks like. It's actually double slot. And this is a PCI, you may be aware that there is a PCI is the IO interface on desktop and servers. So there are 6 links here, each working at 100 gigabits per second. So effective bandwidth of this is 600 gigabits, and it is a 3D torus, means each card will have 6 neighbors, 3D, and 2 neighbors in one ring. So it's like a 3D. So you need some algorithms for routing. Like in the morning we were talking about a ring. So that ring was a one-dimensional ring that was showed by Preeti. But imagine having 3-dimensional ring. So your number of nodes and hops, that will the number of nodes you can accommodate without increasing the number of hops can be much larger. Then I will talk about reconfigurable computing. So it is nothing but a card with an FPGA and lots of memory. So the way it works is, suppose you are trying to accelerate your code, and then if you are using a function which is being used repeatedly, then you will try to optimize it, make it write it in such a way that it takes less amount of time. Now imagine, instead of running it on the CPU, if you could make a dedicated hardware that can do it. Let's say calculation of Lagrange's polynomial, or calculation of some checksum, or searching a sequence in a given set of data. So if hardware could do it, it would be very fast. And this FPGA is programmable, in the sense that now if you are running a particular code, you can download the library through what is called as a bit file. Many of you may be aware that there is a language called hardware description language, HDL, Verilog, or you have earlier we used to use VHDL. So using that language you can describe the algorithms, and not all algorithms can go in hardware, but some amount of some particular type. So you have to study what is whether a particular algorithm is suitable to be put in the FPGA. If you can do that, then with very less compute power you can make that algorithm run very, very fast. So that is the advantage of, so it's an accelerator, and we call it as an avatar. So like there is a Smith-Waterman avatar which speeds up to 200x, and it is put in the BRAF utility about 8 such cards have been put there. So the data is spread across this card and the hardware searches for the given pattern in that. So that becomes very, very fast. So life sciences, fracture mechanics. Another thing that we did was at UT there is a radio telescope and the data is coming in a streaming manner. So many antennas are there. So on the fly they pass through this card and some digital signal processing algorithms are run on it so that the data that you obtain out of it is of relevance to you. So it's for discarding some data or filtering out data is done. So on the fly at the speed, wire speed, you can do the processing. So there are some domains, specific domains in which based on what algorithm you use, you can put it here. So that is the advantage of reconfigurable computing. So it's basically this is what in this biochrome facility, the sequence search algorithm has been put in the hardware that goes into the card and 8 such cards go into a box and then you can parallelly give this, split the data across this card. So all that is done as a part of the programming environment that is available on the bioinformatics machine. So the user doesn't have to worry. He could run the same code on his machine and it may take some time, but here if he does it, it will be faster. So that is the kind of acceleration you get. So that was about reconfigurable computing. So that was about what's happening present. Now coming to the future. So one of the things that we are doing currently and under which this program is also being held, supported by the National Supercomputing Mission. So what is this about Government of India about 4 years ago initiated this 7-year project with an outlay of 4,500 crores with CDAC and IIC being the implementing agencies. So what we do here is building supercomputers, I will tell more about it later, application development, R&D for the next generation mission and HR development. So 3 types of systems are being built, entry level, mid-range and large supercomputers, and the total thing should be about 50 petaflops, that is what is envisaged. That will depend upon the funding available, so it may be 40 or it could be 60. Then this is what we are also planning to overlay upon NKN what is called as National Supercomputing Grid. So what will happen is as a user, you will be able, through this grid, you will be able to access the system that is available to you. So currently what is thought is, like these supercomputers will be spread across the country and a cluster will be formed. Let's say IIT BHU has a cluster. So all the institutes, let's say Allahabad and all those regions, they will be using that. There's one at Kharagpur, so maybe all the computing users in West Bengal and nearby places will use that. That is what the model is thought about. And it will be, the policy will be declared soon. What the policy essentially envisages is certain percentage, 60% or 65% of the compute time is for the host institute, which is giving all the facility to put that supercomputer. Rest of it, like 40-35%, will be available to all the other users. So just hang on for some time. Maybe that policy will be declared by the government and CDAC will implement that. So then there is application development, and I also told you about the manpower development. So another good thing that is happening is that we are doing what is called as a Make in India approach for building the system. So including the motherboard design is going to happen in India. Network design we are also doing. So aim is that all this while we have been importing the systems and just value adding it and implementing them. We want that right from grounds up, like we did in the first mission. We should be doing that, and that is what this Make in India tries to do. Then these are the application areas in which currently work is going on, and there is a consortia for everything. Like computational biology, there is a consortia of members who have been assigned the task of developing. So this is already started in this, like climate modeling, disaster simulation, chemistry, astrophysics, big data. So these are the areas in which applications will come in. So like some of you were thinking of what is the future for HPC, if somebody does a course in HPC, what is the future? So wherever these applications will be used, development of that, maintaining them, all these things kind of work will be offered to those who have some expertise in HPC. Then R&D, again I will not go through this. These are some of the areas in which ISC is front-ending it, and they are shortlisted some of the projects to be done under this. HR development activities, the goal is very simple, that we want human resources to spearhead the activities. Like you are one of them, you are the ambassadors who will take it forward. And for HPC development, for managing systems, so we are looking at undergrad, PhD masters. CDAC is also running a PG diploma course in system administration. So the aim is that at least 20,000 students and faculties and researchers should be aware of HPC before the mission ends. And what we want is that the universities should have it in curriculum. So we have also made a model curriculum which we can share with faculties. And there are various aspects, like not only the concepts but languages, tools development, hardware, network development. So all that is being done by CDAC. We want people who will have expertise in that. So now the systems that are under NSM, I mentioned that 3 of them have been installed already. Param Shivai was inaugurated by Honorable Prime Minister in the month of March, and now I think soon it will be available for users. Similarly, IIT Kharagpur, Param Shakti. At the last one, I think it's maybe next week it will be inaugurated at IISc Pune called Param Brahma. Similarly, IIT Kanpur, Hyderabad, then JNSC or Bangalore are the next 3 institutes to get it. Similarly, like next phase is also planned. So the Technical Advisory Committee of NSM will decide where all these systems will go. Okay, so I will also quickly tell you what are the trends worldwide. The recent list was released in the month of November. So from that, so this is all sourced from top500.org. So there is no change in the top 10 systems in the world. They continue to remain same as the previous one. But newer systems have been added. As a result, if you add all the power of all 500 systems, it comes to 1.65 exaflops. So it is 1.65 into 10 raised to 18 floating point operations in the second. And the system at 500 number is now at 1.14 petaflop. Last time it was at, so there is a change. So new systems being added. As I said, the system which was at possibly at 460 is no longer in the list because there have been some draining off from the bottom. Which are the top 2 systems? Summit. So yesterday I said 160, but the actual HPL result is about 148 petaflop, and Sierra, which is a LLNL, so that has got 94 petaflops. So both of them are based on IBM Power 9 CPUs and V100 GPUs. Together they give this much compute power. Number 3 is in China called Sunway Tihao Lite. So it's just under 900 petaflops. They also have another system called Milky Way 2A, so that is 61. And the 5th one is at Texas Computing Center, which has got about 23. So like this, the last system 500 will have 1.14 petaflop. So we said that there was no entry in the first 10. So where was the first entry? It came only at rank number 24 with 8 petaflop. It again uses Power 9 V100, same as the other top 2 systems. So which country has the maximum? That is 227. That is China. Earlier 6 months ago it was 219. So obviously the share in US is falling. It has come down to 118. But you add the cumulative compute power, US is at number 1 and China is at number 2. Because the top systems are in US, so obviously the aggregate compute power is more here. Then Japan is 3rd, like this United Kingdom comes with 11. All other countries including India, single digit, India has 2 systems only. Then if you look at what CPUs are being used, then Intel's processors are present in 470 systems. Remaining ones are at IBM's Power, then AMD and ARM. So these are the other architectures which make up the remaining 30. And till last list there were no ARM systems, but today 2 systems have entered, but they are at lower. As far as accelerator is concerned, NVIDIA is the one. So if there are 145 out of 500 systems which use accelerators, out of those 145, 136 use NVIDIA. There are few more, some use FPGA, some use AMD's accelerators. As far as the network is concerned, 258 systems use Ethernet, 1G, 10G, etc. and 100G also, I think. Whereas InfiniBand is in 28%, 140 systems. But InfiniBand is present in the high-end systems, Ethernet is present in the low-end systems. There is, as I told you, there is another metric called as how many flops per watt. So in 1 watt, about 16.9 gigaflops are being delivered by the greenest computer called as A54FX. I think this is in Japan. And the second one comes close at 16.3. So in future, you will see more emphasis on greener systems, and because if you want more compute power, you can't afford to keep adding the electrical power. So that's it. 4 minutes, 5 minutes for questions. Yeah, one question.
Benefit from these supercomputers, do we always need to write explicit programs to run on it, or will a program running on a normal commodity hardware will work there as better?
Okay, so the question was can an application which is running on a simple desktop, can it run there, or do I have to write explicit parallel programming? So I will answer it in 2 ways. One is that there are, if you look at the users of supercomputers, most of them are domain experts. They have much knowledge about their domain, be it bioinformatics, physics, chemistry, but they may be able to do Python programming or simple serial programming, but they are not very good at extracting the parallel performance from a parallel machine. So this problem is tackled in 2 ways. One is that to make a particular application run faster or adapt it, how that algorithm can be put on a parallel machine. A domain expert and a team of domain expert and computing experts sit together, and the actual work is done by the computing experts, but they take inputs from the domain experts. So the requirements are given by domain experts, and they will also, in the process, they also know how things are happening, so they also give suggestions, and thus that's the way one can design a good application ab initio. That is one. Second thing which BRAF does is that you take out the complexity out of that running code, etc., by putting a wrapper around it, and you call it as a problem solving environment, or wherein in that I haven't mentioned it, but you can even make a workflow that first, given this data, first run this algorithm on it. The output of that should go to another one, output of that second one should go to third, and finally you visualize or something like that. So you are actually able to make that chain, or how you want to do it. So just by dragging and dropping. So that is the front end, wherein not only parallel computing experts, but people who have knowledge of how programming from browsers or databases, all this knowledge comes into picture. And the new thing that is happening is AI and ML is being applied to these techniques. Like we have a team in CDAC which is working on applying AI to bioinformatics, because huge data anyway exists. What patterns can you find in it? Anything that you can derive out of it. So I am not an expert on that, so I may not be able to tell you what exactly they are doing. But AI and ML techniques are being applied to many of these fields, because inherently these are like you have a situation of big data available to you. So you can mine that data and draw some inferences. Yes. So there have been attempts of automatic C to parallel. That kind of, there are available. I think one team in CDAC is also working on it. That given a serial code, it will look into parallelisms and try to parallelize it and run it on the hardware that you have. But I was telling somebody yesterday that that is after all a program. And what human mind or a person can see parallelism in a given code, that computer program will do it at a limited extent. So as a proof, to prove something, you can do it. But then you cannot beat a human being doing that. But yes, in some cases, for sake of proving or something, there have been attempts like parallelizing, write a code in C or Fortran, it will look for some pattern in that where parallelism can be incorporated and do that. Similarly, I talked about reconfigurable. There are some programs that convert C to VHDL, but again they cannot be as efficient as one actually looks into the C code, figures out which portions of them are actually suitable to be put in a VHDL language or HDL language and do it. So yes, attempts are there, and you will find some papers also. C to parallel kind of things people have tried it, but in my opinion still, a person doing it who understands how, like you have been undergoing this course, after doing that, you know what are the ways of doing it, and if a person like you does it, it will definitely be much better than what a program can do it. Because somebody has written that program, and that program will always behave in that same manner, whereas as a human being, you may find things, look at it in a different way. See, at hardware level, I had told you like a superscalar is one way, wherein a serial code becomes parallel when it enters the CPU. Okay, so superscalar, multi-core. But when you have multi-core, either the OS or somebody else has to do it for you, or of course you can do it through the explicit manner. So at hardware level, I think you can say that superscalar is the only automatic way of that the hardware doing it, in my opinion. But others, other hardwares like multi-core or clusters, they make it available to you, but either user can do the parallelization or the framework like OpenACC, you give directives and then the framework does it. In case of MPI, it has to be done explicitly. So in those cases, the human intervention comes into picture. Yeah, so to give an example of that, I think you should search for how EPIC works, explicitly parallel instruction computing. So Itanium was a implementation of EPIC, which is also combined with what is called as VLIW, very long instruction word. Okay, so the compiler generates that very long instruction word where instructions are parallelized, and so what superscalar was doing in hardware, the VLIW plus EPIC does it in the compiler. It has its own disadvantages, but unfortunately that Intel, Pentium 4 Intel said, publicly declared that no more Pentiums, x86 is dead. They declared, I think in 2000 or whatever. But AMD came out with another, what they did was they made a 32-bit register 64 and they call it now EM64T. So which now Intel also had to follow it, because what happens is if the world were to go for Itanium, they would have been required to invest in the new softwares because it is not x86 compatible. Whereas theoretically a code written for 80386 is Intel guarantees that it will run on it's binary compatible with Core 5 because the ISA is same, instruction set architecture, what Swayam told you. So that is same, whereas Itanium has an entirely different ISA. So world did not want to move over, Intel wanted, and Intel was right because that's a much better architecture. See, this is a CISC architecture, and the other day I think it was not mentioned, but RISC is the way forward because it's a much efficient architecture, and EPIC is somewhere in between that. It takes good things of RISC, it takes some good things from CISC, and thus that architecture is born. So it is a good architecture, but unfortunately, I think 99% of world's desktop and server class machines are x86 today, be it AMD or be it Intel. So it's not easy to shift to an entirely new architecture. Otherwise, if Itanium would have been successful, like world would have moved, then you would have that the way that you are talking, that kind of thing to some extent, but not. It's only for one CPU. Okay, it's not. We are not talking about a cluster or something. All right. Thank you, and you can talk to me later too. And I think they have time to finish their assignments now, right? Thank you.